This video is an introduction to graphs of reciprocal functions. They're of the form y equals 1 over x. Now you might be able to see straight away why they're called reciprocal functions, because it involves the reciprocal of x. Just be aware that they're also referred to as hyperbolas. In particular, we're doing what's called a rectangular hyperbola, which has, you'll see this done properly in just a minute, but very roughly a branch there and a branch there. Okay, there are other hyperbolas that are different, perhaps like that shape, like a cooling tower profile shape, or this shape with the axes there somewhere. We're not doing those last two in our studies. Okay, that's for a more specialized locus study. So that's the basis of what we're going to do, and we're only doing an introduction. Basically, we're looking at just dilations and reflections in this video. We're not looking at translations, although it is possible to use those transformations. So dilations and reflections, which are to do basically with the shape. Okay, so we're only dealing with the hyperbola's shape and not its position in this video. Okay, you can see in red the basic shape that I was referring to there for the hyperbola. You can see that the graph is y equals 1 over x, and you can see the two branches I was referring to before, a lower branch and an upper branch, which never meet. Those branches do not meet, and what they do approach is what's called an asymptote. Now the asymptote is an imaginary line. On this particular hyperbola, it's running along each of the axes, so there's a blue imaginary line there, and I don't mean the axis, I mean something that happens to be on top of it, and the hyperbola approaches that without ever reaching it. Now it kind of looks like over on the side that it is approaching the axes. So if you look at that, it does appear that it's sitting on the axis, but it's not. We can zoom in and then we see closely, oh, it doesn't, oh dear. So it doesn't actually ever approach that, and we can see that numerically by using a spreadsheet or a table and plotting y versus x for y equals 1 on x. That's shown here on the spreadsheet. So we've got in this column x and in this column y, and we have various values of x and various values of y equals 1 on x. And you can see that they get pretty small, the y values get pretty small, but then as x approaches bigger values, the y values get smaller up to here, and then they hit this funny little symbol. Now what do you suppose that means? That's an error on Excel. That means you've tried to divide by 0, you fool. You can't do it. It's not defined. And that's an explanation about why the asymptote exists. Y equals 0, sorry, x equals 0 is the y-axis. Okay, so x equals 0 is the y-axis. If we come back here, okay, that's where my cursor is, and it won't ever approach that because you cannot divide by 0. Why doesn't it reach this horizontal asymptote, which is basically the x-axis? Well, it's a different reason for that, and the reason there is you can see as the numbers, as we get past 1, we now have defined values here. 1 over 1 is 1, 1 over 2 is a half, 1 over 3 is a third, a quarter, a fifth, a sixth, a seventh, an eighth. So they're getting smaller as we increase x. If we get a really big number in there, 60, we get a very small number. It's not 0. So that's because you'd be trying to solve an equation for y equals 0. So 0 equals 1 on x. Now that's impossible. You can't do that. There is no value of x that will make that 0. Remember, if you tried to divide by 0 on there, it's undefined. That's that result there. But to get each of the branches as it comes out to hit the x-axis, which is y equals 0, it's not possible. So y cannot be 0 because there's no solution when you set y equal to 0. There's no solution for x. So getting back to our graph, we have our first dilation, our first transformation, which is called, as I said, a dilation. And the dilation is, you might have heard that word from previous studies, but a dilation is when you change the shape. It's like a stretch. So dilation. And in this video we're going to look at dilations that are negative and positive. Now, negative dilation is a reflection. So if you make A, which you can see over here, equal to a negative value, you've got what's called a reflection. So they both change the shape, and dilation is sort of a stretching, and a reflection basically changes where the branches are. Let's have a look at that. So if we've got y equals a over x, a is set to 1 at the moment, so you can only see one graph, and we'll make that blue. Alright, so it's the same graph as the red one we had there. But look what happens when we change a to 2. So we now have the graph of y equals 2 over x. So y equals 2 over x, it has a different shape. So it's sitting up there, and it kind of converges on this branch here. As you get into bigger values, it does converge with the red, but it sits up further, and on the bottom branch too the same thing happens. So as we increase that, we can see the shape changes, and it's like being pulled in the vertical direction. So as we go out here, we can see its effect. It's like if it was being pulled vertically, so up and down, and it gets pulled outwards. So if we take it back down to 1, which is our base case, and then we look at negative 1, it's a reflection. So this graph would be the graph of y equals negative 1 on x. It is a reflection of the original graph, so you can see that the blue and the red are reflected in the y-axis. We can combine a reflection and a dilation together. So that's what parameter a does. If a is positive and it is bigger than 1, then we get a dilation, which is like being pulled in a vertical direction. If we have values that are negative, especially less than or negative 1 or less in particular, that's all that this video is covering. We're not talking about fractional values of a in this video. You'll get the same effect, except for that we have a reflection. So basically it basically puts where, if you have a look at this column here, column C, basically the negative a, if a was negative 1, so that would be like a equals negative 1. Whoops, a equals negative 1. I've got my negative sign. Here we go. You can see that's what it would do to the y values. Okay, so all the y values would be reflected in the x-axis, and we saw that just there. You can see that we've got, going back that way and zooming in a little bit, we've got this branch here gets reflected to that branch there gets reflected to that branch there. A couple of quick examples. If you had to sketch y equals 2 over x, basically you know that it's going to be dilated compared to 1 over x, and it's not going to be reflected. And what you'd be best doing is basically substituting x equals 1 and x equals negative 1 for these, and you can get two easily calculated points. So the point 1, 2 there will be on there, and the point negative 1, 2 will be on the other branch there. And just use your knowledge, it's not reflected and it's dilated out because y equals 1 on x would be traveling down there somewhere. Okay, so there's justification. For the last example, y equals negative 3 over x, you'd use the same thing. You know that it's a reflection and it's dilated by a factor of 3 as well, so it's got two things happening. And again, just sub in x equals 1 and x equals -1, and you get these y values. So you sub it into the equation given, this one, and you get those values out, and then you can do a reasonable sketch because you know the basic shape.